So simple hardware section will have to turn GBP or else to becomes input, whatever you think I should call it. I don't have a slide about me. You may have something already. Joe FitzPatrick. We did talk yesterday at PCI Express stuff. My background is electrical engineering. I've always had an interest in Preset and other stuff, but really I'm an electrical guy at heart. I spent about 8 years doing hardware pen testing, debug testing, hardware pen testing, and tool development for server and desktop CPUs. That's kind of interesting me, but it's a very big, complicated project, and a whole lot more low-hanging fruit in the hardware security world. So I left about a year and a half ago. Tinkering with all sorts of stuff since then. The other thing that I do is I teach a class, software exploitation via hardware hacking, or hardware exploitation via XPX. Just even really it's a 4-day class, and we basically deconstruct hardware. And this material actually went into some of the class as well. I started working on this project about a year ago. So, maybe you're familiar with side channels. Are you familiar with software on side channels or hardware side channels? Okay, so basically, what is a side channel? We have a function, and we give it input. And normally, the way we test things is we see, okay, the input gives the right output. Right? We're concerned about input output. Right? If functionally the output matches what we expect for the input, it works. Right? If we put in an undefined input, we probably get an undefined output. Right? Security is a lot of playing with these inputs and outputs to use your desired input, your corrupt input, or something else to give you an unexpected output. Function is what does the work. So it's software function. Service can be anything, or it could be a piece of hardware. But how long does it take? When we're talking about hardware, how much power does it consume? Right? Does it react to temperature? We do this on a hot day. Does it work with a little bit? How much EMI does it give off? Right? Every time you have electricity flowing and switching, you give off electromagnetic radiation, right? Which you can measure. Does function affect function G and H I? Right? What about G H I bid? Function X affected by X and Y. If we have a long X, does function have to take longer or shorter or generate more heat or any of those things? So what is the big deal about hardware? What is a hardware side channel? Why is it any different from a software side channel? Right? Well, does network latency help to hide side channels? Yeah, it does. There are ways around that. You can aggregate things. You can, for example, you can cancel out the market repair. Right? You have a couple seconds of latency, and you're trying to measure something that's on the order of microseconds. Difficult, but not impossible. It does obscure. It makes it more difficult. You need to have to track things over and over again to make it work. What about software latency? We're no longer talking about two separate systems connecting over a serial link with some protocol. We're talking about how long does it take a piece of code to run? Right? When you're running it on a gigahertz processor, every instruction takes a fraction of a second. If you have a couple extra instructions in there, does it make a difference? If you have to fetch memory in there, does that make a difference? It does. It's measurable, but it's pretty complicated, right? Hardware permits observation, though, with very fixed deterministic latencies, right? When a bit goes over a bus at a certain time, that bit goes over the bus at a certain time, right? If you're looking at it with a logic analyzer, it's going to show up, right? When you have a series of transactions on a bus that happen in order, right? Generally, they're going to happen in the same order, in the same clock cycles, right? So if you have two things happening in a row, you watch several cycles on a bus, you see, okay, I have two wait cycles between my read and my response, right? My read request and that gives you information about what actually happened. Right? So, what's the state-of-the-art approach? Right now, people are using really expensive scopes. Like $10,000 somewhere, and it probably costs £20,000 because taxes and all that stuff. Expensive probes, a single probe to connect to a single set of pins, a single differential oriented probe, they run $2,000 to $4,000, right? It's not cheap. But you also have expensive software. You know, you're doing a lot of data processing, you need MATLAB, you need a commercial license for MATLAB, it's money. And smart people. You need people who know math, who know statistics, people who know electronics, for all this stuff together. And you need to understand the underlying function that you're attacking, right? A lot of people talk about, you know, extracting keys from encryption. You have to understand encryption. So, you generally have to understand encryption to do that, right? I don't like encryption. It's a complicated thing. So you also kind of customize a whole bunch of software to glue all the pieces together, automate your equipment, and make it happen. So there's nothing wrong with that in my perspective, right? How many of you have seen someone talk about a hardware side channel at that conference? Anyone? So like Colin, Flynn, and Jasper, I'm one of two guys that I've seen a couple times. Great, but they're talking about pretty fancy stuff, right? Encryption is complicated. I don't understand encryption. I get the idea, I know how it works, but I don't really care about those details. Math is hard. I can add and subtract, but I try to avoid anything beyond that. Actually, subtraction I get mixed up sometimes. Money is really expensive. I don't buy all the scopes and stuff. Actually, I recently got a really good deal on Tektronix oscilloscope, and it was Fry's is a chain in the U.S. that sells electronics. And they had a floor model oscilloscope that had been on the floor for 8 years, and they're clearing out that line. They're not going to get any more replaced. So if they keep reducing the price until it sells out across the country. Right? Well, they couldn't find the one in the store because it was in inventory, but they didn't know where it was. They kept going, bugging the guy. He finally found this scope wrapped up in bubble wrap. It's been on the back shelf for like 4 years. But I got this $4,000 oscilloscope for only $200, so it was worth it. And I actually live right down the street from Tektronix, so I brought it to them and they serviced $100. So I got a brand new calibrated $4,000 oscilloscope for $200. Anyway, yeah, so equipment is expensive, money is expensive. And really the result of this is anybody who's not a hardware person who goes and tries to learn about hardware side channels, it's not accessible. It's difficult, it's out of scope for what a lot of people are like, oh, who's going to like decap my chip and use an EM probe to measure something? You know, someone might do it, but it's actually not that complicated, right? So I want to come up with some good side channels for every man, woman, and child, and the kind of thing that anyone can understand what you're doing and why, and actually reproduce at home, right? So in the U.S. we've got this new thing, the Common Core curriculum, right, which is a big controversial thing where they're trying to standardize the curriculum across the entire country, and all grade school students go through. So I don't know, maybe side channels can get up in that at some time. Why not? So I talked a little bit about complicated stuff, and then there's some high-end embedded systems that run full operating systems these days. It's a Eagle of Life. But all the way down in the corner, I have it's an Arduino Pro Micro. It's an Arduino board, paddle board, but it's pretty minimal. It's like it's tiny. It's like that big, right? And it's got an ADR, 328B chip on it. It's got a serial port to program it and do other stuff, and it's got a whole bunch of I/O. It's pretty simple, but it's actually a pretty common chip. Actually, this is the same chip that is in the thermostat at my house. Right? I have an electric baseboard heat, and I have these programmable thermostats. You get the regular programmable thermostat where you set a temperature in the morning and temperature at night. Or you can spend like $20 more and get the 7-day programmable one, right? Which has 7 zones, so you have Monday plan, Tuesday plan, Wednesday plan, and every day of the week, like different date times that your heat changes. But they both are exactly the same hardware, and they both have this chip, and they do block me from downloading firmware, but they didn't block me from updating fuses. So I can just rewrite the fuse that turns off the block on firmware download, and then I have firmware. So I got my 7-day programmable thermostat for $20 less than it costs. But again, the point is, this is a chip that's used in the real world in electronics that people use all the time. So my budget, I replaced my $20 bill with a £10 note because I don't actually know how much
1.63.
That's my guess. Is that?
1.63.
1.63. Yeah. Yeah, I was thinking like, oh, what the exact number would be, but it's not there. Just call it sometimes, right? So let's simplify things. Sorry. So timing attacks are kind of the easiest in my opinion, right? So what this thing over here is, this is a CY7C68013A mini board, right? This is a chip made by Cypress. It's called the Easy USB. It's the Easy USB FX2. It's a USB 2.0 system on chip. It's got a little microcontroller core. It's got a whole bunch of I/O. What's really cool about this chip is you can stream data. You're using DMA with no code, just stream data straight in over USB. And so this chip is the core of a whole bunch of kind of low-end logic analyzers, like the display logic, right? But it's also it's a pretty cheaply available chip. So here's my other Soleil logic. This is the one that's $5 from China. It's a knockoff, but it doesn't actually work with the latest software because they've realized people are cloning their hardware. So it's the same chip inside, similar to that board. That's a reference board. It's got a few more pins, but same idea. You got a little chip, you got a bunch of pins, you hook them up to wires, and you run some software. So this software is PulseView, which is part of SIGROP, which is an open source logic analyzer software for all sorts of things. It actually supports a wide range of test equipment. But the point is, I'm using a cheap board. I got these for $5 each. But the chip, if I wanted to buy just the chip and build my own board, the chip itself costs $15 in the US. So I don't know how that works. And I need some code to attack to draw this board on the Arduino board. And if you go to Arduino Playground, which is kind of their source of libraries to use, there's this nice password function, which lets you set and get a password. So I went and got basically the sample code that they ship with it, and I looked through it, and there's this password evaluate, right? Is the current guest password equal to the target password? We've got a nice little loop here. It's going to go through for 1 to the max password length, or so 0 to the max password length. We'll compare, and as soon as we get a mismatch, we fail, and if we don't get a mismatch, we pass. Make sense? I mean, that's kind of how password checking works. And we're talking about this. This is an 8-bit microcontroller, right? It's a Harvard architecture, which means that it's a very simple design with very limited instruction set. We're writing this in C, but this compiles out to lots and lots of code. And this is about the complexity that microcontroller should be capable of. Anything real cryptographic is kind of more difficult than it's likely to happen on a chip this scale. They do make versions of this actually on crypto accelerators, so maybe that's not completely true, but yeah, this is a hobbyist type thing. So I put together some hardware, and that's my old version. I actually made a little CD for it now, the new one. So I'll give you a little demo of the setup I've got. This is more or less the default code I downloaded from the library. If we wanted to enter in a keypad, 159 star. So we get all reds. Like 1, 2, 3, 4. Hit a star. Greens. We'll give it 1, 2, 3, 4. And that's all there is to it. I mean, I took this board, added some lights, and added a keypad. The keypad is driven with the library, also from Arduino Playground, and actually it's a password sample program already using this keypad library. Make sense? I mean, this is actually really the scale of what you might find in an actual inexpensive safe. This is the caliber of the hardware and the software. So preparing for observation, I got the logic analyzer, I got the little probes that can clip on. This is before I had a nice little board with breakout pins for everything. And we need to time things. And so, to show you again, basically every time you push a button, the lights change. Right? And this is a serial programmable LED strip. So it only takes one pin, and that one pin sends out a serial waveform that addresses all these individual lights, and it changes colors. So every time I do that, 1, 2, 3, 4, right? That was 4 different bursts of activity with that display, right? And then when I hit star, it's going to go through a series of them. So it's 8 separate steps where, first you press, that's 1 green, and then 2 greens, and then 3 greens, 4 greens. So, if you look on the diagram, over here we have a key press, and then we have the LEDs flashing, right? The way the key press works is we've got this, we've got a bunch of rows and a bunch of columns, and when you push a button, it crosses a row and a column. The processor is constantly triggering pulses on each of the rows, each of the columns, and it's constantly listening on each of the rows, right? So it goes pulse, 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 pulse while it checks pin 1, and then pulse, 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 check pin 2, pulse, 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 pulse. And when it sees the pulse, it knows which stage it's in, and it knows what key to press. So what I'm looking for right there on the key is I'm looking for anything that is in the 4th row. So this green line, this pin is hooked up to pin number 4 of the keypad, which is pin number 4 of the keypad, right? So, button, and then there's a delay. What happens in this time period?
That's what you.
So it's running that piece of code we just saw before. It's evaluating. It's doing the process of comparing the password before it spits out a green light for pass or a red light for fail. So what it is, I tried a couple things. So if I press nothing, if I just start with nothing and I hit star, it fails, right? Well, how long between those 2 events? Using the logic analyzer, you can zoom in until you get really precise measurement. And it was test time, 19.13 microseconds. And then I type in 0 characters. Oh, sorry. I got it right. I figured that one out. Oh, sorry. I gotta figure out what I meant. Anyway, this is the part I know makes sense, right? If I got 1 character right, it takes a certain amount of time. If I get 2 characters right, which means so 1 1 1 1 1 1, right? Only 1 character match. 1 2 2 2 2, 2 characters match, right? It's gonna take a little bit longer because it's gonna go an extra iteration of the loop compare, right? And then 3 characters, 1 2 3 3 3 3 3. Got 3 characters match. You're gonna finally 4 characters match. 1 2 3 4, so on and so forth.
Is it?
The first line is no characters entered. The second line is a character entered but not correct.
Oh yeah, 0 matching. That makes total sense. Thank you. And that's why you guys are here. So what we see here is when we have 1, 2, 3, or 4 characters, each additional character takes 1.3 microseconds of comparison time, right? And that's not a lot, right? That's not something you can visually see, right? But when we've got a logic analyzer, we hook up to it. This little logic analyzer that costs $5 to $10, right? It can sample 24 megahertz, right? To get this data, it's good to sample, so 1 microsecond is about 1 megahertz. It's good to sample 2 to 4 times more than you need. So really 4 megahertz sampling is all you need to have this sync, right? That's well within the abilities of this chip. And actually, like, you can do it with 1 megahertz sampling, and you can get close enough to realize the difference between a pass and a fail. You won't always get it in 2 tries to do it, though. So this. So again, what about the real world? I didn't take my safe, but I bought this safe at Harbor Freight, which is a hardware store that sells lots of really low quality direct ship to China. But it's cheap, so I got a safe for $20, to play with. And it's, they come up with their cool brands too. Public Health Security kind of gives that nice, like, cookie party fundamentalist, like, appeal. But I don't think they realize that, did anybody know who won the Battle of Bunker Hill? It was in the U.S. it was the British because there was some confusion over whether they should be defending Bunker Hill or retail, and yeah, stupid Continental Army doing their silly things. Yeah, so Bunker Hill, people think, yeah, that's America, but that's also a loss for the growing colonies. Anyway, just funny things you encounter. So I peel this little green pad off, and what do I find? It looks almost exactly like this keypad. And actually, this one actually has a sticker backing, so you can stick it over an ATM to do your skimming and stuff like that. And you know, same thing. It's a 3x4 keypad instead of a 4x4, so it only has 7 pins to look at. And I keep opening it up, and wow, look, you know, this is old school. Like we got big, huge diffs instead of these tiny surface mount parts like that anymore, which makes it even easier. And you know, pull it out, and I didn't figure out what my controller actually is, and who knows what it actually is. But you know, essentially, it's doing the same thing. It's scanning a bunch of rows, it's reading a bunch of columns, and it's recording, and then it's doing some sort of algorithm to check your password, which is almost timing. So an interesting thing about this, the way it's designed, these LEDs stick out, and this capacitor charges up and triggers a wire that releases the solenoid and grabs it. So you could actually, if you were very careful, you could actually stick a little wire in there, and we should just down behind it and trigger the capacitor, and which is opposite of that. So you don't have to do this stupid side channel stuff. Whatever. So yeah, I'm sorry, yeah, the solenoid. Oh yeah, the LED. As I was mentioning before, we're looking at this, the output to this little display. This thing just has a little light that flashes instead. So you just take a wire out and behind the value going into the LED letters. You could actually do it without doing that. You could use a photosensitive thing.
Optocoupler.
Yeah, optocoupler. And it should be no problem. The safe also beeps. Right? So really, you could actually do some acoustic stuff there. Now, here's the interesting thing though. What's the audible frequency range?
50 to 20 kilohertz.
Yeah. So it's 15 to 20 hertz to 20 kilohertz, right? 20 kilohertz. So most audio stuff, again, it maxes out at 44 or 96 kilohertz, right? That's much lower than the resolution of the timing we need to hear, right? So does that mean we can't do it? So here's the thing, if you have a higher end audio chip that's actually doing high-end sound and it actually is doing 96 kilohertz sampling or something like that, you probably wouldn't be able to, because that chip is going to be clocked at a certain rate, and you know, no matter where you start the sound, it's always going to be played synchronous to that 96 kilohertz clock. On this level of stuff, here's our little speaker. We have a little chip that's just going to start putting a square wave to that speaker to make noise, right? So we can actually find the start of that. I'm kind of how can I explain it. You can listen for the sound, and the sound will start at a much more precise edge than 20 kilohertz. Does that make sense? So, but that's complicated. So you trigger the solenoid. So let's fix it, right? So what we could do is we could put this. Evaluate. So we have this password function. We do the evaluation. Before we do the evaluation, we set up a timer. This watchdog timer is something that basically triggers every periodic amount of time. It's at 15 milliseconds, right? And the purpose of watchdog timer is usually to reset a system. You have something that's critical and crashes, right? It just sits dead, right? So a watchdog timer is a register that you have to constantly update, saying, yes, I'm still alive, yes, I'm still alive, yes, I'm still alive. And if you don't update it, your system will reset and start over, start your code. So you get some crash recovery system. We're actually not going to have it reset the system, we're just going to have it like wake from sleep. So we set the timer up here, 15 milliseconds, then we do our evaluation, right? So the key press is before this timer. Then we go to sleep and we just sit there and wait for that 15 milliseconds to end. And then we start flashing lights, right? So what we've done is we've taken this variable piece of code and we put it inside a 15 millisecond block, right? So there we go. We've done something to make it so that if we want to do a simple timing attack. The time you push the button to time the light flash is always going to be just over 15 milliseconds. It's not going to be the Is that good enough? Or not? What are we doing in here? What code are we running? Okay, in this case, we're actually going to sleep. We're sitting idle. Another common thing to do is, calculate the number of instructions and just run a bunch of no-ops. Right? What's the difference between a no-op and an add or a subtract or a multiply or divide? Which one is actually doing something? Not the no-op. So let's move on from time into power analysis. So back to the state layout approach. We got expensive scopes, expensive pros, expensive software, smart people, custom software. There's actually this guy Colin O'Flynn, who I finally met last month. He's got his cheapskate approach to side channels. And cheapskate, actually this whole setup is incredibly cheap for what it's capable of doing, because it's not $10,000 plus $2,000 times 5, that's $200. This whole system is $1,500, and it's all the software's open source, all the hardware's open source. It's free. And it's designed to basically have a high-speed analog digital converter, right? The PC. He plugs into this, which is a FPGA-based board, that samples it, stores it into DRAM right in there, and then you hook it up via USB to your system to download data. And this box is actually mostly this inside the box. It's got two separate AV channels and some other logic inside. But yeah, again, I'm really a cheapskate. I'm not just a cheapskate, I'm really a cheapskate. So I made this little board, and I don't know if you got my business card. I have a new one now, but I still have a few of these. Chips. So there's a populated. It's the call it FitzPatrick, because it's fits, and it's the simple power analysis. You're not scared by schematics, we'll go over this, okay? What we do is we have hooked up to our system that monitor that we're going to talk to the power that's going into our test system. This thing right here, this triangle, is what's called differential amplifier. Right? It takes two values, it subtracts them, and then it amplifies that difference. Right? The idea is when you have noise, usually your noise is similar at your points. So if you measure two sides of a resistor as power is being supplied to the board, all the noise is going to cancel out. And so we just get a clean measurement of how much current is going to that resistor. We amplify it because we're looking at small changes and we want to see a big value. So we can set the gain of this circuit, that little thing that looks like a rectangle little hammer is this device here. It's got a little screw terminal on it. It's a potentiometer, so you can adjust the gain how much you amplify the difference. It goes into this other chip, which is AD converter. So it takes an analog signal in and spits the digital signal out. It goes out to these pins. This header on here is the same as the header on here. You hook your cable to these two, so you can hook your logic analyzer to this board. And we still have not broken the bank because the cost, well, I figured the cost for this whole setup is like $5 to $10 US dollars. And then this board plus all the components populated is just under $20 US. Except that was 6 months ago, and this one chip is discontinued or available, so I have to revise it. So it goes. So 1850 US plus shipping. Whole bunch of components, some service called soldering. It's fun to practice. Yeah. I had never done service called soldering until just over a year ago, and I'm completely comfortable with it right now. It's not the easiest thing in the world, but it's actually not magic. So, of course, I have a bunch of boards that come out. There's a couple of choices you can make with what chips you use. And you can also choose different resistors if you know you're going to have a large power consuming system or a low power consuming system. And there's one big chip up here. This is a voltage regulator that generates from USB power, which is 5 volts, it generates plus or minus 10 volts. supply, because that's what this chip needs. It needs a really wide positive and negative range so that it can amplify properly. It's one of those perks of analog. So this is like the only analog circuit I've designed in my life. It actually worked, which is surprising. I stick to digital stuff for this one. So, you know, if you don't want to do that, you can get one of these. 7-inch split eBay and chain. And if that's too complicated for you, there's no uses for this board. So, shunting. If we look at this red box is our target system, our data board. And we put this little resistor over here. And so we have power going into the system. It goes through a resistor, and then it goes into here. As this box consumes more current, right, we get a larger voltage drop over here. Are you guys familiar with V equals IR? Okay. So more current goes through, larger voltage. That voltage, these 2 points, we measure the difference between them, amplify that, and that's what tells us our relative value. No accuracy involved, but lots of precision. And we've got a couple headers over here, which is how we hook that up. So power supply comes over USB, goes to this regulator, has a little bit of filtering, and then goes out to your system, and then comes back after going through this little resistor right here. This is pretty common. It makes a lot of sense to shunt your power supply. But the other strategy is you shunt your ground, right? Because theoretically it's the same thing, but actually what you might find out is that you can amplify a signal more when you start with ground, and it's also a cleaner signal when you shunt the ground instead of half a voltage. So you just move this jumper over, designed to use those schemes in case one network. And then I modified a target board, one of these here. Basically, it's a. This is one of these little boards. It's tiny. It's zoomed in, and on this board is a voltage regulator that's going to make sure that this chip only gets the 5 volts in this kind of panel. There's also a couple other capacitors that keep everything else stable on the board. Capacitors are like buffers, right? They hold the charge so that when you start drawing more power, it spits out more power, so you don't have a droop, right? If you draw more power, you sometimes might get a little droop, so your voltage instead of being 5 volts might dip down to 4.5 volts when you're doing a lot of work, and then back to 5 volts when you're doing nothing. Capacitors kind of buffer that and keep the voltage consistent. But I took all of them off. Just to make it a little easier to see what I'm looking at, because I want the voltage to droop. I want that voltage to change when I have more power being consumed. In the end, I actually found I didn't even need to do this on this platform. I was actually able to get precise enough information without capacitors. So this is my old setup. Again, I've wired it up here, and got another one here where you can see I've soldered resistors directly to the board. It's a little easier to use. And I set up this populator board right here, hooked it up to my logic analyzer. Again, I was originally thinking I was going to put this chip in the logic analyzer right onto this board, but I ran out of space, and again, I could buy the chip $15, or I could buy one of these ready-made for working for $5 for that one. So let me know how it works. Wire everything up, and the first thing I wanted to do is I wanted to characterize instructions. So if any of you use Arduino before, what I really love about Arduino is it's like it's a one-click download, install, everything, and that gives you the compiler and the programmer and everything. And you know, if I'm doing anything serious with a microcontroller, I'm going to use something else. But for someone who needs to remove all the barriers and needs like a quick instruction, a quick like let's make this the biggest path between like writing a line of code and flashing a light. Arduino is excellent, so I use it a lot for these demonstrations. So what I did is I used the blink program to turn the light on and off. But what I did is I put a bunch of code in between. First, it's inline assembly, and I do a bunch of additions over and over and over again. Then I have some inline assembly, and I do a bunch of no-ops over and over again. Right? And adds, they're grabbing 2 separate values, so they're using logic to combine them, and they're writing a result. Every time you switch a voltage inside of a chip, you have switching current that you consume. Right? So this is using lots of switching current. No up just increments the program count. That's all it really does. So there's a lot less switching current instead. And this is a really poor way of displaying it, but I haven't written a free software front end yet. What it is, I took the most significant bit of the AD converter, and this is the trigger. And so what happens is we have adding, and then we have adding and nops. And so this first section here is adding, and we can see we have varied power consumption. And then look at right here, we have this big empty period of time, right? Low voltage, low power consumption. That's our no-ops. Right? And then we actually have to loop back over. We have adds again, and we have no-ops. You also notice that there's this little delay from the edge of this edge to this edge, and one of those spikes, this edge to this edge, two of those spikes, this edge to this edge, two of those spikes. Arduino has a lot of overhead. We're writing something in C that's being compiled into assembly, being run on this device. Actually, this is a thorough instruction of the device. It runs at this one that I have runs at 16 megahertz, one instruction per clock. It actually does have a pipeline, so it's always preparing the next instruction. So if you do a branch on this device, basically all it does is a branch says, ignore the next instruction. Right? So you have a bit test set, and the next instruction might be a jump. Well, you test a bit, if it's true, then you skip the next instruction. If it's false, then you execute the next instruction, which is your jump. So pretty much every instruction takes one clock cycle. 16 megahertz, it's pretty easy to go through stuff. And as I mentioned before, I showed you the loop. That loop was a couple lines of C code. That loop compiles down to about 20 instructions. Right, 20 instructions at 16 megahertz gave us that 1.3 microsecond time for each iteration of the loop. And it does it every time, very consistently, which is great for sure. So the other thing about it is just sources of noise. And what I'm actually seeing is on all of the channels, there's this noise that's periodic, and that was actually updates for LEDs, right? So basically, you gotta take away anything that's distracting, that's irrelevant, because on this system, the most power-hungry devices are these LEDs, right? Each one of these LEDs is taking like 3 or 4 times as much current as the CPU running. And also even the power LED, that one's always on, so it's consistent, steady state. But these, anything that changes over time, is going to mess up your measurement. So on this guy, I just put a jumper, so I'm going to flip off the jumper and turn off the LEDs. On my older system, I just literally pulled the pins out so we're connected. So pretty software front end. Blank. It's a software problem, someone else's problem. Anybody interested in writing free software front end? Actually, this program that I'm using, SIGROC and PulseView, they actually now have analog support. So that's what's great about an open source project is that everything have to do. So back to lock. So what? I should plug in my laptop. These guys. Give it just a moment. So I'm drawing a blank on this slide. So we had an idle period, and I'm not remembering what I did to measure the idle period. And I'm looking at the different lines of the AV converter, and you see there's a lot of noise. So this is the most significant bit. Actually, that must be, oh yeah. So this is the most significant bit right here, right? 0, 1, sorry, other one. Looking over. 15 milliseconds is this long, pardon me. This little notch right here, and this notch right here, and this notch right here, those are our 15 millisecond delays, right? That's where we are using minimal amounts of power, right? And that's what you see. What I did measure is actually zooming in on just this. I don't have a slide for that, I apologize. But I zoomed in on this 15 millisecond delay, right? And I told you what we did is start the timer, we do our comparison, and then we sit and wait in a low power state until we're done, right? That whole period of time takes 15 milliseconds, right? Well, the sleep time is variable, right? So the push button to the light flashing is fixed, but the fall asleep to wake up is going to be less when we have more code to execute. So we're turning the power side channel back into a timing side channel. We're just measuring the timing of this little pulse again. Does that make sense? Okay. So we've got our little table. We measure the beginning and the end of the idle. This is where having a really capable logic analyzer comes in helpful, because we have a very large difference along. So we're looking at 17 childs per microseconds.
What is the trigger here? I mean, when you find out that the register is set, so you start your actual power measurement, because you are combining the timing and power measurement.
Yeah, so our trigger is going to be when we go and start consuming a whole lot less power.
Okay.
And our endpoint is when we start consuming
that is
power.
built into the software. Actually.
No, it's manual. So what I did is I looked at this and I said, okay, well, it's very clear to me that this most significant bit, it only periodically is low. So basically what it is I set a trigger on is the most significant bit, and that was sufficient. And what I can do is I can adjust the potentiometer so that when I'm doing normal execution, the most significant bit is high, but when I do that slow sleep mode, the most significant bit is low. Does that make sense?
But normally it should be like automatic, right? Because here we have the chance to do it manually. Sometimes we don't have that control, so we have to find a way to automate or start our measurement.
Yeah. So I mean, if you're going to do this in any volume, you want this automated. But you'd also do the effort of like actually converting analog signals from digital data into a waveform and trigger on that. So.
And the second question is, what is the optimal, regardless of our oscilloscope's maximum sampling rate, what would be the optimal measurement for our program? Like we have like 40 megahertz, but our device is like, let's say 2 megahertz. Is it always good to put it on like maximum sampling?
If your system is up to the speed to do it, and the amount of data is not a problem, just send it all the way back.
Okay.
In all reality, when you're doing this, and you know the long capture and path of your data space is going to be limited, your ability to search for data is limited. So if you can figure out the length of time that your critical measurement is, so in the previous case it was how many microseconds does it take to go through that external loop, 1.3 microseconds, and then you multiply that by 4, and that is pretty much guaranteed where we need. If you do it less than that, it gets more complicated. It's still visible, but not really reliable. If you want to do it automated and all that stuff, you want to do foolproof. So, back to level. So, I went through, ran out with different combinations. We're looking at a matter of 17,000 microseconds, 17 milliseconds difference. And which makes sense, right? You have a pause of 15. Again, we're working with a low-end rank controller with a big variable clock, right? So its calibration is not perfect. We'll say 15 milliseconds of delay, we get up now. We actually got closer to 17 milliseconds. But when we're looking at 17 milliseconds, our order of change is tiny. It's 1 microsecond. So that's one of the reasons why having precise measurements is really helpful.
Sorry, is that one measurement, or is that a whole bunch average? Because if your clock's that variable, it's hard to, is the system actually that deterministic?
So when I say variable, I'm talking parts per variable, right? Any one clock actually is quite precise. It's usually like 10 to 100 parts per million reliability. But the difference between this clock and this clock is going to be a whole lot bigger than the difference from this clock, now versus in 5 minutes, or now versus when it heats up, or now versus different power condition. Right? So yeah, that's a good thing to be aware of, but it encountered limits. So the numbers were very consistent if I ran it over and over again in one system. and they would be different but consistent when I ran it over environment. Does that make sense? Yeah. So I did make another enhancement to it. I put a second geometer on there, and what that let me do is change the offset so that I can amplify more, because when it's zero based, right, when zero is when a low power state is closer to zero, right, so I subtract an offset, then I can amplify it greater and use the whole dynamic range of my inverter for power precision. So I didn't do this with the logic analyzer using this cold oscilloscope, and it kind of gives you a better grasp of what you're looking at, right? We have execution, we go to a low power state, and then we power back up. We have a nice spike here because I can call capacitors on. Right? So yeah, that was one of the improvements I had in mind. Pretty software would be really nice. Actually, a little clock offset would be nice. And integrating that logic analyzer would be cool. But yeah, basically, we get to this point, right? We've done our comparison right here, right? We know it's a low power state. We resume low power state, so we measure from here to here. We subtract it from a previous sample from a different key pattern tree, and this will vary, and this will let us infer how much time is spent running this pattern. Does that make sense? So, yeah, rolling this. Oh, do I finish right at noon, or do I have one more?
Sorry, I couldn't hear you.
Do I supposed to finish at noon or before noon?
Perfectly honest, it's up to your audience in this one because it's on right after.
So there's more. So if you look at all sanction tax, there's passive and active stuff, right? There's invasive and non-invasive, just depending on how much you want to modify the system. So we talked about some timing analysis, right? And a little more invasive, we actually took off the caps, so it's tweaking to do more invasive stuff. So active of actually stimulating input would be what glitching is, right? We're going to start playing with the clock in the system, or you know, the recent pin or other pins in the system. You're gonna poke at it electronically out of spec and not focus on data to change how the thinking is. But then there's invasive stuff which just take the chip apart and rewire it. So for £20 or about $20 or about 10 pounds we do some glitching, right? Good. So this is the safe operating region of an AVR 18 through 2018. Right? This is the spec, and it said basically anywhere in this range you're fine. You can go anywhere up to 5.5 volts. We do need 1.8 volts. But if you have 2.7 volts, you can only leave it up to 10 megahertz. Beyond that, it might not work. Right? In all reality, the boundary is something like this. Right? They have, a market guarantee reliability right here, and then you go out here and it changes. I've found, one of the things that they say, okay, 16 megahertz at 5 volts, or 8 megahertz at 3 volts, 3.3 volts. I found no problem running at 16 megahertz and 3 volts on any 18 megahertz. So when you do cross this extra line, though, that's where things fail. Things don't work right. So if you find an optimal condition, that's when you're right at the edge. You're running as fast as you can, with a millivoltage you can. And if you want to do a voltage glitching, right, that's where you lower how much voltage you supply for a brief period of time and you don't get average. Right? If you want to do frequency glitching, that's where you speed up your clock for just a very brief period of time and you get into a value condition. Right? The idea is you want to get into one of these conditions at a precise time, right? So where and when. If we go back to what we're doing here, we have a bunch of comparison, and then we finally get down to an extent, right? Everything we do, we narrow it down into one comparison, one single assembly instruction. It's going to determine whether the task fails. So that is what we want to target with glitching, right? The idea is that instruction is going to work if it gets its full, what is it, 1/16 megahertz time to execute. If if we give it less than that, can we make sure it doesn't work and so that it fails in the opposite direction? So there's some tools out there that you can use. The Dazzle is a pretty cool system. It's FPGA-based with a little ARM core on there. It's great for doing fuzzing of embedded systems and some glitching as well. It's got some specialized hardware knowledge for that. However, it's too expensive. It is $8,100 US dollars. So it's out of my super cheap stately. This chip we talked about before, right? We use it as a logic analyzer or streaming data in. It can actually go the other way too. It can spit data out. But if we're at 24 megahertz, right? 24 megahertz is not going to be enough for us to do a glitch, right? The board is running at 16 megahertz. So we need to likely make something significantly less than 16 megahertz, smaller than 16 megahertz, larger frequency, smaller period than 16 megahertz. So it's too slow, right? We could also go path with lower voltage, getting 10.4 megahertz and glitching so that way. So the idea is the glitching device is going to output a clock, right? And we have an interrupt pin that we tie to a trigger, right? So we know like an LED is going to flash a certain amount of time before this critical instruction. So what we would do is we would actually find the last key press and count the number of assembly instruction key press and that if statement, right? And try and glitch it, right? So we have to configure around the way. So what happens? We have this trigger happen. This is when we press our key. We have a software delay, and that's going to generate a pulse, right? And that pulse can be logically combined with our actual clock to give us like an extra 2-minute clock. So the clock is running along 16 megahertz, 16 megahertz, 16 megahertz. And there's one cycle that goes at 32 or 64 megahertz or something. It goes a lot faster than the clock cycle. Fast enough that it fails, right? And it doesn't skip the next instruction, it executes it. And so we can escape that passive evolution. Generally, when you have a block of code like this, it's either going to do one or the other. It's either going to fail true or fail false for any given architecture, right? So you might be out of luck. You might have this if pass fail, or if not pass fail, you'll never be able to glitch it. But if it is if pass fail, you will. Again, that's something that varies greatly depending on architecture. In order to try and get something like this working, we're going to need some programmable hardware. So I've been looking around at what I can do this with, and the best way to do anything is to find a quantity piece of cheap hardware that does it. And no one knows it just does glitching, right? You can just go down like Best Buy and buy a glitcher, buy here, whatever electronics store and buy a glitcher, right? Well, actually, this is the Matrix glitch board. It's a glitch chip for Xbox 360, right? So it essentially is a consumer device, a mass-produced consumer device for the purpose of glitching, right? So this is straight out of the doc on how to use it. The idea is the Xbox 360 boots up and it loads a blob of code from a flash chip, and it checks the signature on it. And if the signature doesn't match, it's the system, it doesn't execute. If the signature does match, then it executes. Right? So what some smart people figured out is that we have sort of the CPU PLL bypass pin. So this glitch chip has VCC and ground, and then a BCDEF pins that you open up your Xbox 360 and you solder these pins to designated spots, which, if you got all that fine SMT soldering is difficult, this is kind of insane. So we assert CPU PLL bypass. What that does is actually slows down the clock on the CPU significantly, right? We wait for post 39 to start. So post is a power on self-test. Just like a PC, it goes through a series of power on stages. They're all numbered, and the number is the state is actually output. So if you wanted to plug a device in, it shows you on the LED display what state you're in. So what this does, it actually hooks up one of these pins to one of the pins of the post output. and actually knows exactly when closest to stage 39 starts. As soon as close to stage 39 starts, you start a counter. When that counter reaches a precise value, like so specific event that varies based on conditions of the console, you send a pulse on reset. We just talked about clock glitching. This is reset glitching. We're going to pull the reset signal really fast while our clock is going really slow, right? So normally you say, oh, if we're going to reset, hold down the reset button for a while, and the clock keeps going, and everything has time to reset. What we're trying to do here is just reset the things that are close to the reset pin, and the things that need to propagate to them actually receive the signal. And then you deassert this bypass, then everything goes back to normal. And if you were lucky, you pulled that reset at just the right time when it was comparing, or when it was deciding, do I halt or do I continue? And if you're lucky, usually sometimes you plug this system thing in and you run and you go through a boot with 2 minutes, and it goes over and over and over again, waiting until it actually glitches and lets you code. But once you do that, then you're running your own inside code and you can start making backups for providing games. I've not played video games in like 15 years, but I still have a lot of video game consoles that I play with. Not many of us. So if we look at the, let me pop over and show you the glitcher thing. So this is the code right out of this GitHub that is running there. This is VHDL, and basically goes through the steps I just described. Basically, if you have a rising edge in your clock, then you go through and check, and you do a bunch of if statements to check to see what stage you're in. And first, if you're, I'm not going to go into the details. So it's basically we check the post bit, it tells us what post we're in to determine when we're in the right stage, and pass it on. We have a counter that we start, and the counter just increments. Count plus 1. If you're not familiar with VHDL, it's not really like any other programming languages. Basically, this is a whole bunch of logic that happens all the time. It's like every time any one of these bits change, it's like a function. Every time one of these bits change, like a function gets off of the pathway. Right? So every time you have a clock cycle, every time there's a clock trigger, everything in this block runs at the same time. And so this count equals count plus 1 gets run every time the clock cycle triggers, right? And then once you have a post count that's in the right value, then you actually try and do the bypass, and you can reset the system and trigger it at the right time.
Can we get the weather?
Quite a little in-depth, don't worry, because it makes sense to you, but that's what it looks like. So back to our system. We're here doing another test program, and this is normally it's a program that just blinks the light. But what I had to do is I had to turn the light on at the very beginning, and it goes into a loop, and a while true, and it does nothing. It's just waiting true to not be true, double true. But when it's done, after infinity, it turns the LED off. Right? So basically, what we're going to do is we're going to have it keeps getting checked, and if we can manage to glitch that if, right, we'll jump out of this loop. If we jump out of the loop, the light will go off, then we know we win, right? So I don't really know how this works. My objective was to actually have my badge doing this, but I didn't get that far.
You gave your badge to my wife.
What's that?
Technically, you gave your badge to my wife.
I did. All you guys were too kind, you kept getting me drinks instead of letting me get back to it. Sorry. That's this stuff. But this is like the code, right? It's a little bit less complicated. This is Verilog, this is HDL. I prefer Verilog just because I've been doing security validation of Verilog for a long time. So we have an input of a clock, an input of a trigger, and an output of a clock out, right? And So somewhere I have a board. Actually, this is a test board. This is the matrix switch board. They're almost exactly the same. This one has a 50 megahertz clock chip on it. This one has a 100 megahertz clock chip on it. So that's what I've been using. Otherwise, they're nearly the same board. So we have a 100 megahertz reference clock, and we decide what we want to output as our base clock, right? And I chose 12.5 megahertz because I did that along with lowering the voltage to get it right in the edge of the failing region, right? So we have this block here. Basically, every time the clock changes, this block runs, right? And we have a counter that increments. So this counter is 26 bits, right? That increments. So it starts at 0 and just add count. And we look at the second bit number 2, third bit. And what that's going to do is tell us, so every 2 clock cycles this is going to increment, right? And then each bit up doubles it. So counter 2 is means clock out is going to be 12.5 megahertz clock, right? But then all the way down here I have this if trigger. So in the event we sense a trigger, we're going to wait until our counter is this very precise value, which is 1024 clock cycles after it triggers. And this 101 at the end, right? This 1 means that bit 2 is high, our clock cycle is high. And normally we go 101, 100, 101, 1. I can count in binary. 100, 101, 110, 111, and then 0, right? And then we get a new clock phase in our clock. What I did then was I said, okay, we're only going to wait 1 cycle at 50 megahertz, right? Which is a fraction of microsecond. And then we're going to reset our counter to 0. Makes sense? So what's going to happen is we're going to have a clock that's going at 12.5 megahertz. And then when we hit our trigger 1,000 cycles later, it's going to have a clock cycle that starts out 12 megahertz and then bam, goes back down at 50 megahertz. And then we'll resume going at 12 megahertz. Does that make sense? And this number here is going to be calculated so that actually is the right number of impressions to trigger. So beyond that, it's still a work in progress. I got the system set up to do exactly that. Basically, you need to modify this chip. You change a fuse to take an external clock input, which is programmed on one of the pins of this logic board. Hook it up there and test it. And this is a very labor-intensive process. This chip that's on here is a pretty inexpensive part. It has a whopping 32 bits of data to capable of storing, right? So you think about like this microcontroller has 32K of code space. This has 32 bits that we can logically use to store things. It's a very different paradigm from what you're used to with a programming microcontroller. Does anybody here ever program a CPLD or a FPGA? So you guys know. And that's where I'm